can start. So we are very happy today to present in the Q-Flag seminar Stefan Schreierer from Hanover in Germany. Is going to speak about refined, unramified homology of schemes. So please go ahead.
Thank you very much for the invitation. It's a great pleasure to speak here. So, yeah, this is a project that well, it goes on for quite some time now, and I had a preprint in October last year, and then afterwards I realized that at the time I didn't understand things fully, actually. Yes, so today I will try to present the results in a slightly in a more general version than the original archive preprint. And nonetheless, to begin with, I decided to talk for quite some time just over the complex numbers to motivate things and also to simplify notation a little bit. And then towards the end, I will explain how these things work over any field. But essentially what I will say works over any field. Okay, so now I need to be able to, yes. Okay, so to begin with, as I said, for simplicity, I talk at the first part of this talk over C. And then over C, we can look at the cycle class map from the Chow group to cohomology. If X is smooth projective variety and you have a cycle, you can map it to its homology class. And by Poincare duality, this is a cohomology class. Okay, and since we are over C, this lands in a certain subspace. It's not so important in the subspace of Hodge classes. And the problem that we would like to understand is to describe kernel and image of that map. Okay, and then if we are over C, then this problem is completely understood for divisors. That's Lefschetz 1-1 theorem that says that the cycle class map is actually surjective to this piece. And the kernel are exactly the algebraically trivial divisors, so line bundles that you can deform to the trivial line bundle. So kernel and image are completely understood for divisors. So instead of trying to understand the image, we may as well understand the co-kernel of that map here. And Lefschetz 1-1 says that this vanishes for I equals 1, and it's known that it doesn't vanish in general. So for I bigger or equal to 2, there may be torsion elements in this co-kernel. And the first examples have been found by T and Hitzebrook. Nonetheless, the Hodge conjecture predicts that there shouldn't be anything else than torsion, so this co-kernel should be a torsion group. So the upshot is that if we want to understand the image of the cycle class map over the complex numbers, one would need to prove the Hodge conjecture and then the torsion parts of this co-kernel. And over other fields, the similar story would be to prove the Tate conjecture and then prove the torsion, to understand the torsion part of this co-kernel. So today I won't say anything about this rational piece of the question, but only about the torsion, which is somewhat easier. All right, so instead of talking about the image of the cycle class map, we may also ask about the kernel. And the first observation is that the cycle class map factors through algebraic equivalence. So two cycles are algebraically equivalent if you can move one to the other parameterized by a curve. And if that is possible, then the homology classes will be the same. And so the cycle class map factors through Chow group modulo algebraic equivalence. And so instead of understanding the kernel of this composition, we may as well ask for the kernel of this second map, of the induced map. And that's what is usually called the Griffiths group. So the Griffiths group are all homologically trivial cycles modulo algebraic equivalence. Okay, Lefschetz 1-1 again says that over the complex numbers this is 0 for I equals 1. And starting with I equals 2, this is in general not 0. And the first examples have been found by Griffiths. So what's the example? It's a quintic in P4. This is a Calabi-Yau threefold, and this has many lines. And if you take the difference of two lines, each line has the same homology class. So the difference of two lines has trivial homology class. And what Griffiths proves is that this difference is not algebraically trivial, by computing some arbiter-Jacobi invariant and computing that this arbiter-Jacobi invariant or the transcendental arbiter-Jacobi invariant is not zero. And then Clemens looked at the same example and he noticed that there are not only 2 lines, but infinitely many lines. And if you take all possible differences of lines, you get so many classes that in fact, this Griffiths group tensor Q is infinite. So the Griffiths group is not finitely generated. And he does this by combining Griffiths method with a degeneration argument. So a very general quintic has not finitely generated Griffiths group, which shows that Chow group's mod algebraic equivalents are really pretty far from a usual homology theory. So it's not finitely generated up to torsion, even up to torsion. All right, so instead of tensoring this with Q, you may also tensor it with a finite field and ask what happens and how big can that be? And this question is also completely understood. And it's a long story. So it started with work of Bloch and Ogus, which were the first to found a method how to prove that a cycle is not divisible in the Griffiths group. So to prove that if you tensor it with a finite field, you do not get zero. The first example is Bloch and Ogus. And then Schoen realized that one can use this to find actually examples where this Griffiths group tensor a finite field is infinite. And then the question was, for which primes can you do that? And Schoen treated infinitely many, Rosenschon-Srinivas treated almost all primes, but not all, and Totaro treated all of them, including 2. And the example is the Jacobian of a quartic curve in P2. So this Jacobian is a principally polarized abelian threefold. And the theorem says that this threefold has lots of curve classes that are interesting. And what are they? Well, you have the canonical arbiter-Jacobi embedded curve. And then you can multiply with -1 on the abelian threefold. And you look at the image of the curve. I call this C-. And then I can look at the curve minus C-, and this is homologically trivial because multiplication with -1 acts trivially on even cohomology of an abelian variety. So this way you get one cycle, and with these methods established by all these people, well, plus Nori and others, one can prove that this cycle is not divisible by L. And then how do we get infinitely many? The trick is that an abelian variety has a multiplication by n map. And you can push forward this cycle by multiplication with some number. And this way you get infinitely many cycles. And they show that among these infinitely many cycles, you get infinitely many that are linearly independent mod L. So that the Griffiths group mod L is infinite. So it's far away from a in this case, from a indivisible group. Okay. So the remark here is that these Griffiths groups are pretty mysterious. It follows from a simple Hilbert scheme argument that Griffiths groups, which are obviously abelian groups, are countable. So we have a countable abelian group, but no non-trivial group is known to be a Griffiths group. So in other words, we do not know the Griffiths group in any non-trivial example. And so somehow the best thing that we can do is that in some examples, we can compute it if we tensor it with a field. So in this case, it's a countable Q vector space of infinite dimensions. So it's a Q to the infinity, and this guy here will be ZL to the infinity. But that's essentially all we know. We don't know what the Griffiths group itself really is in these examples. All right, so now let's go to cohomology. The purpose of this talk is to explain how one can use homological methods to say something about these groups. All right, and to begin with, I want to define for a K variety X, the cohomology of the function field with values in some abelian group A by the direct limit of the cohomology of all open subsets that are not empty. And here, so let me be vague, later I will be more precise, but here I'll be vague and think about this as the Betti cohomology of the complex points of view with values in an abelian group A. All right, and with this definition, there are residue maps. So if for any codimension 1 point, yes, this has to be a smooth point, sorry, or X has to be smooth. And for any smooth codimension 1 point, there's a residue map that goes from the function field to the function field of that divisor, and it lowers the degree by 1. And with this definition, the unramified cohomology is classically defined on a smooth variety. So I'm sorry, the standing assumption on the slide is smooth, X smooth, even though it's not written. The unramified cohomology of a smooth variety with values in A would be the kernel of the cohomology of the function field. Sorry, is the subgroup of the function field of all classes that have trivial residues. So what that means is that locally at every codimension 1 point, you can extend the class, because this residue map is exactly the obstruction for extending it locally across the generic point of that, or across the codimension 1 point. Okay, so this definition has its roots in rationality problems, and there in the work of Colliot-Thélène and Ogus, who I guess who studied this and introduced this in detail. So if X is smooth projective, then these groups are stable by rational invariants, and they are very useful because, of course, this cohomology of the function field is also by rational invariant, but it's a huge group, and the unramified cohomology is a subgroup that is still by rational invariant and even stable by rational invariant, and it's smaller, so it's more useful. Okay, and then classically, so these groups have classically been studied in rationality problems, starting with Colliot-Thélène Ogus. But then there's also a relation to algebraic cycles, and this has its roots in the Gersten conjecture and the work of Ogus, which happened even before the work of Colliot-Thélène Ogus. And yes, so here for a smooth variety, we look at the sheaf associated. That's a risky sheaf associated to the pre-sheaf that maps a Zariski open to its cohomology. Again, I think about Betty cohomology. And then one gets an array spectral sequence whose E2 page is given by the Zariski cohomology of these curly HQs, and it computes the ordinary cohomology. So again, this notation here is the singular cohomology of the complex points of X. So we have the spectral sequence, and what Bloch-Ogus proved is that the spectral sequence, it's supported in a triangle, and the edge of this triangle has an explicit geometric meaning. So one edge where the P is 0, this is just unramified cohomology as I defined it before. And at the other extreme, where P is equal to Q, the spectral sequence has as entries a Chow group mod algebraic equivalence with values in A. And so this furnished a relation between unramified cohomology and algebraic cycles, because we have the spectral sequence and we can look at edge maps and so on. And then if these two terms, the E20Q and E2QQ are not too far away from each other, it's reasonable that you get a relation among the two, maybe together with the cohomology that actually is computed by the spectral sequence. And that's indeed what happens. So what Bloch-Ogus found was that the second Griffiths group is isomorphic to the quotient of the third unramified cohomology of X, quotient out by the image of the usual cohomology. So what that result shows, I mentioned before that these Griffiths groups are not finitely generated in general. And so we see also that unramified cohomologies in general are not finitely generated, because of course this group here is finitely generated. But one can do more with this result. So let me show you one application, which is due to Mercouri-Suslin. So their proof of Bloch-Kato in degree 2 showed that the cohomology of a function field, let's say here over C with set coefficients, that this cohomology is torsion-free. And since this is torsion-free, it follows that any subgroup is torsion-free. So third unramified cohomology has no torsion. All right, so if you look at the Griffiths group, it is a quotient of this torsion-free group by the image of the third singular cohomology of X. But that is a finitely generated group. So what we find is that the torsion of the Griffiths group has to inject into a Q mod Z to the third Betti number, so to the rank of this group. So in particular, the n torsion for a fixed n in Griff 2 is bounded by the third Betti number of X. So that's what Mercouri-Suslin got got from this description. So this is the first example that shows that unramified cohomology has useful applications in the theory of algebraic cycles. Okay, and then later, when the Bloch-Gatto conjecture was proven by Voisin, Colliot-Thélène and Voisin noticed another striking application of this story. And this is about not the kernel, but the co-kernel of the cycle class map. So recall this Zi of X stands for the co-kernel of the cycle class map. And we are interested in the torsion. And what Colliot-Thélène and Voisin proved was that the torsion so if you look at codimension 2 cycles, then the torsion in this co-kernel is isomorphic to a quotient of 2 unramified cohomology groups. So here we have unramified cohomology with Q mod Z coefficients, and you quotient out all those classes that lift to unramified cohomology with Q coefficients. Okay, so the proof uses Bloch-Ogus theory, so Gaston conjectures as before, plus Bloch-Gatto conjecture. And this had many applications because unramified cohomology can be computed with K-theoretic methods, and so you can prove that the integral Hodge conjecture fails for varieties just by computing K-theoretic invariance of the function field. Essentially, you don't even have to have a smooth projective model. You just look at the field, and you can say something about any smooth projective model with that function field. So this way, for instance, Colliot-Thélène and Voisin found the first examples of rationally connected varieties that do not satisfy the integral Hodge conjecture, meaning where this group is not zero. Okay, and so the natural question here is, how about higher codimension? Okay, and as I said before, so this approach, by looking at this coniveau spectral sequence, is not going to help with that problem, because we have this triangle spectral sequence, and the interesting pieces get further and further away the higher the degree is, and so it will be hard to compare them. So if this approach is not gonna help. Okay, so instead of trying to follow that approach, let's look again at what I explained. So Griffith 2 is related to unramified cohomology, and also the failure of the integral Hodge conjecture for codimension 2 cycles is also related to unramified cohomology. And here we see that each time there is an H3. So the formulas, of course, are different, but one similarity is that it's a codimension 2 cycles are related to a third unramified cohomology. So this we can see here. And yes, so the unramified cohomology is the subgroup of the function field of classes that have no residues. So why is there such a relation between H3 and codimension 2 cycles? And so I claim that one can give an heuristic argument why there is such a relation. And in fact, one can give a simple proof of this relation. And the key lemma is something simple. So instead of the definition that I gave you of unramified cohomology, one can use, or one can, with that definition, one can prove the following simple lemma, which gives an alternative description of unramified cohomology. Yes, it's a simple lemma. So it just says that the unramified cohomology is the subgroup of the cohomology of the function field of all classes that lift to an open subset which has no divisors in the complement. So this is very close to the original definition, but it's global in nature. So the original definition was you look at all classes that have no residues, meaning that whenever you had a codimension 1 point, the residue vanishes. But this globalizes, and if you have that condition, in fact, you have a class on an open subset which in the complement has no divisor at all. So it's a big open subset. And this point of view is very useful when studying the relationship to algebraic cycles. So why is that? Well, let's see. So assume that we have an unramified class. With this key lemma, this says that there is an open subset whose complement has no divisors where the class lives. So the complement has at least codimension 2. Well, okay, but then there is some codimension 2 cycle given by the complement. Okay, so I already have a cycle. And now I may ask, if I have this class on this big open subset, well, does it actually extend also over the codimension 2 cycle? And maybe does it extend to all of X? And the obstruction for this extension will exactly live in codimension 2, and you will get a codimension 2 cycle. So the claim is that if you start with an unramified class here, it lives on a big open subset. If you ask whether it extends to all of X, you get an obstruction that lives, which is exactly a codimension 2 cycle. And the H3 here appears because H3 has the special property that if you have a class on a big open subset whose complement contains no divisors and no codimension 2 subsets, then the class extends to all of X. So if you want to extend from a big open subset to all of X, all you have to do is you have to kill the obstruction in codimension 2. Okay, so the claim is that if you have the class on a big open subset, then asking whether it extends to all of X gives an obstruction, which is exactly a 2 cycle that you can see here. And if that obstruction is trivial, then the class comes from all of X. And so that's why we quotient out here by the cohomology of X. And now what is written here are not codimension 2 cycles, but codimension 2 cycles up to algebraic equivalence. So where is this taken care of? Well, unramified cohomology is not only a class on a big open subset, but the image of that class on the function field. So the same representative on the generic point may have different lifts to different open subsets, that big open subsets. And that's exactly the relation that corresponds to algebraic equivalence. So mapping the cohomology on a big open subset to the function field corresponds exactly to going from the free abelian group of codimension 2 cycles to the free abelian group of codimension 2 cycles mod algebraic equivalence. Okay, so that's the heuristic, but one can make this into a proof and prove this in kind of an elementary way. And in fact, with a little more work, one can also prove this with these kind of arguments. Okay, and then if one looks at these arguments, they don't use the Gersten conjecture or Bloch-Kato conjecture anymore, and are quite basic, so that one may wonder whether one can do similar arguments to treat higher codimension cycles as well. And the answer is yes. And so I will try to explain the setup next. Okay, and now I will make precise what cohomology functor I take. And what it turns out that, okay, so this heuristic that I described here, it's pretty flexible. So I didn't understand this at the beginning, but at some point I understood that this doesn't even need smoothness of X. So it's a very general phenomenon. And so to treat non-smooth spaces, I cannot work with singular cohomology, but I need Borel-Moore homology. Okay, so that's by this definition. So HIX of A, what I mean by this is what I call Borel-Moore cohomology, and it is not really cohomology, but it is really homology. It's Borel-Moore homology in this degree, 2D minus I, where D is the dimension of X. And you take the underlying analytic space, and A is some abelian group. So recall Borel-Moore homology is essentially the same thing as singular homology, but you don't look at finite chains, but locally finite chains. So if X is compact, then this is just homology. And if X is smooth, this is isomorphic to singular cohomology in degree I. Right, so properties. If X is smooth and equidimensional, then this HIX of A is really singular cohomology of the underlying analytic space. So as long if you don't want to worry about singular spaces, then just think about this as singular cohomology as we did before. But remember that if X is singular, then it should really be Borel-Moore homology. Then, yes, Borel-Moore homology, it's not functorial with respect to arbitrary pullbacks, but it is functorial with respect to étale maps between schemes of the same dimension. And we will only need that it's functorial for open immersions between schemes of the same dimension. So we have pullbacks to open subsets where U has the same dimension as X. And then, so there are not many pullbacks, but Borel-Moore homology has a lot of push forwards. So for any proper map, you have a push forward map. And the way I define this Borel-Moore cohomology here, the push forward will change the degree. So it will go from hi minus to C, where C is the relative codimension of this morphism, to hi of Y. Okay, and then another advantage of Borel-Moore homology is that there is a cyclic class map, even if X is horribly singular. And the reason is just that if you have the cycle, you have a subvariety, and you can write this as a locally finite chain, and so you get a map Borel-Moore homology. So there's always this cyclic class map. Okay. Right, so I'm okay. On this slide, I explained everything over C, but there is, of course, an analogous definition of Borel-Moore homology also in Ital cohomology. I will come to this later, but let's stick to C for a moment. Okay, so I will fix this cohomology theory for the rest of the talk and denote it for simplicity just by hi x of A, where A is an abelian group. And now in the heuristic before, what were we looking at? We were looking at a class on some big open subset and asked whether it extends to the points in the boundary. And to formalize this, it's useful to introduce the following notation. So fj of x are all points in X that have codimension less or equal j. And here the codimension, what I mean by this is the dimension of big X minus the dimension of the closure of little x. So it's not the local codimension of X, but it's this formal thing. There wouldn't be any difference if X is equidimensional, but in general, maybe this is a difference. It doesn't matter too much. So we look at all points that have codimension less or equal than j. In this way, we get a filtration, an increasing filtration that starts with f0 and it goes up until f dimension of X. Right? Because if this j here is dimension of X, then I have collected all points. Every point has codimension at most dimension of X. And here's an example. So if X is integral, then f0 of X would just be the generic point. And f1 of X would be the generic point plus all codimension 1 points, and so on. Now, I defined this as a set, but this is really an infinite intersection. So it's an inverse limit of schemes. And so it's a pro scheme, a pro object in the category of schemes. And so part of the story of this talk is that these spaces, they behave pretty well. So we can really think about them as spaces. Yeah. So in particular, they have a well-defined Borel-Moore cohomology. So it works well for them. They are infinite intersections of open subsets where you throw away points of the wrong codimension successively. And since they are this inverse limit, it's natural to define their cohomology as a direct limit. And this works because Borel-Moore cohomology was contravariant. So you have pullback maps for inclusions of open subsets of the same dimension. So that's what we use here. So you can restrict to open subsets of the same dimension. And for this reason, I can define the cohomology of fj of X as the direct limit of all open subsets that contain fj of X. So here we run over all open subsets that contain all codimension j points. For instance, if X is integral and j is 0, then we would just have the direct limit over all open non-empty subsets. And we would just compute the cohomology of the function. Okay, and yeah, one more notation. So for a scheme point, little x and big X, it makes sense to define the cohomology of that point. In the notation above, it would be f0 of the closure of X. And what's this? This is just the direct limit over all open subsets in the closure of X. Yes, and you take the direct limit of the cohomology of all these open non-empty subsets of the closure of X. sometimes I also write, instead of little x, the function field of little x. Just a notation. Okay, so we look at this natural co-niveau filtration of the scheme X, and each piece has naturally associated to it the cohomology groups, and these are huge groups because we take this direct limit, and these are huge groups. So what can we do with this? The point is that whenever we have an algebraic scheme U and a closed subset set with complement V, then there is a Gaussian sequence. This is just the long exact sequence of the pair in Borel-Moore homology. So there's always a sequence like this. With my convention, it reads exactly like that. So you restrict from U to V. Then there's a residue map to the cohomology of Z, shifted by something. And then there's a push forward map to the cohomology of U. And that sequence is the key player, because the problem we want to address is, given a class on some open subset, does it extend to a bigger open subset? And the sequence exactly says that, well, it does if some residue maps are zero. All right. And then looking at this sequence and doing a simple double direct limit argument, one gets the following lemma, which compares exactly the cohomology of fj of x and that of fj minus 1 of x. So why do we get such a lemma? Well, direct limit functor is exact. So you can play, whenever you have some exact sequence, you can apply direct limits and get something exact. So for this reason, the cohomology of this fj of x is pretty well behaved. And we get that lemma, which says that if you have a class on fj minus 1 of x, so a class defined on all j minus 1, codimension j minus 1 points, and I ask whether it extends to all codimension j points, so it comes from the left, then this is exactly measured by a residue map to the cohomology of codimension j points. So the obstruction lies exactly at codimension j points, and I get some classes in the cohomology of that point or of the function field. Okay, and then the next map is a push forward map and so on. Okay, and with this lemma, it's now natural to generalize unramified cohomology, to refine unramified cohomology. And by this, I just mean the image of this morphism here. So that's refined unramified cohomology, maybe of refinement index j minus 1. So the index up there lets me remember where the unramified cohomology group sits. So this is a subgroup of fj minus 1 of x. And it's given by all points that lie in the kernel of this residue map, or in other words, that lift from j minus 1 points to j points, codimension j points. Okay, and an obvious corollary of this lemma here is that the zeros unramified cohomology is the usual unramified cohomology, because if j is 1 here, then here I have f0. If j is 1, then here we get I minus 1, and here we have the sum over all codimension 1 points. So we get back exactly this formula of the definition of unramified cohomology. So this is a generalization, and it works well for x pretty arbitrary, separated of finite type over C. Okay. Yes. So the first result is that with this setup, so recall that there is a cycle class map to Borel-Moore homology, and I hide these Borel-Moore homology groups with this notation. So there is always a cycle class map. And you may ask about the torsion of the co-kernel, and this is computed by a quotient of two refined unramified cohomology groups, one with Q mod Z coefficients and one with Q coefficients. Okay, and now if you plug in I equals 2 in this formula, what we find is that the co-kernel of the cycle class map for codimension 2, so that the torsion in the co-kernel of the cycle class map for codimension 2 cycles is isomorphic to a quotient of zeros refined unramified cohomology groups. But the zeros refined unramified cohomology is the usual unramified cohomology. So we get back this formula, and that's exactly the formula of Colliot-Thélène and Voisin. But now, okay, so this original result of Colliot-Thélène Voisin used Bloch-Ogus resolution, which needs X smooth. But the arguments I presented work also for singular schemes. So this is okay for any separated scheme of finite type over C. And it also works for arbitrary codimension. And what is surprising is that, in a sense, the proof is simpler. So it doesn't use, it uses only simple ingredients. Simple ingredients from homology theory, so Ogusian and Bockstein sequence, and then there's one ingredient from Ital cohomology. You need Grothendieck-Silbert 90 theorem. Okay, but there is no Bloch-Kato used here or Bloch-Ogus. Okay, so once one has this result, we remember that there's this result of Bloch-Ogus, who computed the Griffiths group of codimension 2 cycles, and it's natural to wonder whether there's also a generalization in our context. And there is. And for this, I should define what the Griffiths group of an arbitrary algebraic scheme is. But it's the obvious thing. So you look at the cycle class map in Borel-Moore homology, you look at the kernel, and then you divide out algebraic equivalence. So this makes perfect sense for every X. And if one has such a separated scheme of finite type over C, then the first result is that indeed we can compute the Griffiths group in terms of refined and ramified cohomology, and it will be a quotient of some refined and ramified cohomology with set coefficients, and we quotient out the image of usual cohomology, which again is Borel-Moore homology. And the second result is that if we look at torsion cycles, then there is a transcendental Abel-Jacobi map. So if you have a torsion cycle, you can associate to it, in the Griffiths group, you can associate to it a homology class in H2i minus 1. And you quotient out some piece of the Koh-Niveau filtration, which is defined by all classes that die if you map them to fi minus 2 of x, meaning that they die if you take out codimension I minus 1 subvarieties. So you quotient out some piece of this Koh-Niveau filtration. And there's a well-defined map like that, which, if X is smooth projective, agrees with Griffiths' Abel-Jacobi map, which of course is only defined in the smooth projective case. But this Abel-Jacobi map on torsion cycles is a general thing that works also for singular spaces. So there is such a map, and we can compute its kernel. So the kernel of that transcendental Abel-Jacobi map is related to refined and ramified cohomology. Yes, it's some unramified cohomology with Q mod Z coefficients, and you quotient out, there's a certain G filtration on this group, and you quotient out a certain piece. So I don't want to go into these technical details, it's not so important, but there's a well-defined filtration in terms of the Bockstein map. And yes, so you have to quotient out a certain filtered piece to compute the kernel.
What does transcendental mean?
Yes, so transcendental means that so Griffiths' Abel-Jacobi map is a map from the Chow group to so you look at a homologically trivial cycle, and Griffiths maps this homologically trivial cycle, associates to it an element in some torus. And this map is not defined. So this map is not necessarily zero on algebraically trivial cycles. So the Abel-Jacobi map does not descend to Chow group modulo algebraic equivalence. And then what people call the transcendental Abel-Jacobi map is where you quotient out from this torus a certain abelian subvariety, which exactly corresponds to the image of those classes that are algebraically trivial. So somehow, if you have a family of cycles parameterized by some curve, then the Abel-Jacobi map gives a map from the Jacobian of that curve to the torus, and you have to quotient out all these images. And if you do that, then you get a well-defined Abel-Jacobi map on Chow group mod algebraic equivalence. And in this formula, this corresponds to the fact that I'm quotienting out this piece of the Konivo filtration. So Bloch has an algebraic way of defining the Arbitrary map on torsion cycles, really on the Chow group, not mod algebraic equivalence. And what he would get is he would get a map to this group, not to this quotient I've written. And the transcendental indicates that I'm not starting at torsion cycles in the Chow group, but torsion cycles at the Chow group mod algebraic equivalence. And so I have to quotient out something to make the map well defined, otherwise it wouldn't be.
Thank you.
Okay, so this, this result here, 1, uses similar methods as before, but 2, to compute the kernel, this needs the Mercury-Suslin theorem, so Bloch in degree 2. And the remark is that 2 is motivated by work of Voisin and Ma, who proved this in the case I = 3 when X is smooth projective. Their formula is slightly different, but they prove some formula along these lines. So this was the motivation for the second item. And yeah, it simplifies these works. So Voisin and Ma used Bloch in general, and our approach only needs Mercury-Suslin theorem. Okay, so I'm slow. So what can we do with this? Some applications. Let's AI of X denote the Chow group mod algebraic equivalence. Then a simple corollary of these complicated looking formulas before is the following. So if X is a separated scheme of finite type over C, D is the dimension, then the Chow group of codimension 1 cycles mod algebraic equivalence injects into Borel homology via the cycle class map. Plus the co-kernel is torsion free. So in particular, if you have a torsion class in here, it must be algebraic. And the second result is that the torsion in the Griff 2 injects into a certain quotient of Borel homology. And the proof is simple. So you look at the previous formulas and just notice that if this refinement index is negative, then these groups are 0 by definition. And in these special cases, one gets that certain co-kernels or certain torsion in some co-kernels is 0, so you get these results. And these things are well known if X is smooth projective, but yeah, I think the case of singular schemes is maybe new. Yeah, I think it's new. So the first result here is an analog of Lefschetz-Bon-Bon, and this is an analog of the Mercury-Suslin theorem I've explained before, that there's not too much torsion in the case where X is smooth projective. And here you can get explicit bounds also in the case where X is arbitrary. Okay, so another application of the story is to torsion in Griffith groups. And this, okay, so the first question you may ask is, well, are Griffith groups always torsion free? And in fact, it took quite some time until people found the first torsion, non-trivial torsion class in Griffith groups. So this was 1992, a paper of Schoen, which is quite delicate. So he has a very delicate geometric construction. And he finds some cycle that he constructs via some Chern classes of some complicated vector bundles. And then he can prove that this cycle is torsion and has non-trivial arbitrary invariant. And you see this is tricky, because if you have a torsion cycle, its arbitrary invariant is going to be constant. So you cannot use normal functions where you take derivatives of this arbitrary invariant in families. So it's tricky, but Schoen manages to do this. And this way he finds torsion classes in the Griffiths group, actually in Griff 2. So what remained open after Schoen's work was whether you can also find torsion classes that are not detected by the arbitrary invariant, so by a Griffith method. And Totaro, in his Champs paper, he used cobordism theory to construct torsion classes in Griff 3 that are killed by the arbitrary Jacobi map. So there are also classes that are in the kernel of the arbitrary Jacobi invariant. And similar examples have been found by Soulé and Voisin. Then okay, so then there was this paper of Soulé and Voisin that also found some torsion classes that are killed by the arbitrary Jacobi invariant. And then the story went on in a slightly different direction. So people observed that if you don't look at the Griffiths group, but at the Chow group, then there may be infinite L torsion for any prime L. So one may think that this is, so Chow groups, of course, may contain infinite torsion, like an elliptic curve has infinite torsion in Chow 1. But for a fixed prime, it will be finite for the elliptic curve. So it's reasonable to ask whether the L torsion is always finite. And this is not the case for Chow groups. But in all these examples, these classes, they are all algebraically trivial. So they do not give infinitely many classes in the Griffiths group. So it remained a basic open question whether Griffiths groups have finite torsion, or whether the torsion subgroup is finitely generated or not. And I've explained earlier a result in a positive direction. This was this Merkurjev-Suslin theorem. And now I want to formulate it slightly differently. So Merkurjev-Suslin theorem says that this transcendental arbitrary Jacobi map, which starts at the torsion classes of the Griffith groups, and it maps to H3, where you quotient out a certain piece of the Konevo filtration and tensor it with Q mod Z, that this arbitrary Jacobi map is injective. And since this is injective, and these groups are finitely generated, what we get is that the end torsion of the Griff 2 is always finite. And since that map is injective, by the way, we also see that in Griff 2, the only way you can, the transcendental arbitrary Jacobi invariant is the only way you can detect, in some sense, a non-trivial class. But in Griff 3, you can have things that are in the kernel. That's what Totaro proved. Okay, so there is some finiteness statement for Griff 2. And now in this story, I want to present two results. And to explain the first, I want to take advantage of the fact that we worked with separated schemes of finite type over C. You may say, well, I mostly care about smooth varieties, but I want to show you a case where it's really beneficial to work with singular varieties. And this is to define the following, or to study the following Konevo filtration. So X can be arbitrary, but you may assume that X is smooth, no problem. It's interesting in the case where X is smooth. And then Nj of the Griffiths group, I want to define at the image of the direct limit of all Griffiths groups of codimension I minus j cycles on subvariety Z of X, where Z itself has codimension j. So I'm looking at cycles on a subvariety, codimension I minus j cycles on a subvariety, which itself has codimension j. So the cycle viewed on the big ambient space has codimension I. So in other words, I'm looking at a cycle in the Griffith group and I'm asking, well, does it lie on a subvariety? And how big is that subvariety? Now, naively speaking, if you have a cycle, of course it lies on a lot of subvarieties. I can just take a hyperplane section and it's going to lie there. But I'm not asking that it lies on this subvariety just as a cycle, but as a homologically trivial cycle. It has to be in the Griffith group, which means that its homology class on that subvariety is trivial. So if you have a cycle, you cannot just take a hyperplane section, because if you do this in a random way, that cycle on that hyperplane section is not going to be algebraic, not going to be homologically trivial. So this is really a non-trivial condition here, and we get a non-trivial filtration. And what one gets is a decreasing filtration. So N0, if J is 0, then I can just let X set be equal to X, and I get all the Griffiths group. So N0 is everything. N1 is some subspace and so on, and it ends at the Ni minus 1. So this is one result of the theorems before, that the Griff 1 of Z, even if Z is singular, is always 0. And for this reason, Ni minus 1 is always 0. So I mentioned before that this is the point where it's where we benefit from the fact that we can treat singular schemes, because even if X is smooth, here I'm forced to run through all the singular subvarieties. So these sets here are really singular. It would not work if I take the resolutions of these sets. I would get a different filtration that has not so good properties. So the first theorem corresponding to torsion cycles is that I can compute the N1, the first piece of this filtration, on torsion cycles. And what is it? So the N1 of the torsion subgroup of the Griffiths group is the kernel of a certain transcendental arbitrary Jacobi map from the torsion cycles to this piece. So this is not exactly the transcendental arbitrary Jacobi map, but it's a quotient of it. But maybe this is not so important. This is because the transcendental arbitrary Jacobi map, as defined before, I'm not quotienting out N1, but maybe Ni minus 1 or so. It's a certain transcendental arbitrary Jacobi map. And the kernel of this is exactly N1. So if we put I equals 2 here, we exactly recover the Merkurjev-Suslin theorem, because N1 Griff 2 is 0. And then we exactly get that the transcendental arbitrary Jacobi map is injective for codimension 2 cycles. And this is a generalization. And what it says is that if we have a cycle on X that has trivial arbitrary Jacobi map, then it has to be supported in codimension 1. So it there must be a divisor, and the cycle must be homologically trivial on that divisor. And this is a non-trivial result. So I've shown you some examples, but I haven't shown you the examples, but I mentioned that there are torsion cycles. So these Griffiths groups have torsion classes. And in all these examples, it's not obvious that there is a divisor that contains these classes. So it's a non-trivial result. And well, the reason for this is partly that it uses Bloch-Kato conjecture in the full strength of the Bloch-Kato conjecture. So it generalizes Merkurjev-Suslin theorem and does use Bloch-Kato. All right, so what we find is that no matter what the codimension is, if you look at the N torsion, then up to finite index subgroup, this N torsion must lie in N1. So you can go from M0 to N1. And then this almost looks like an inductive way how you can show that the Griffiths group has finite N torsion. Okay, but this is not the case, and the second result will show this. So the first result showed that the torsion is finite in some sense, in the sense that it is supported up to finite index subgroup in codimension 1. It remained open whether the torsion is finitely generated. And well, the answer is no, it's not finitely generated. And the example is this. So S, a very general Enrique surface, and C, a very general quartic, then we can look at the product of the surface with this Jacobian of the quartic. This appeared before. So this was the abelian threefold whose Griff 2 is infinite if you tensor it with any finite field, or with any set mod L, say. Right, and what is new here is this Enrique surface. So if you take the product of the Enrique surface, you get a fivefold. And I claim that there are many codimension 3 cycles, so surface classes on this fivefold that are all 2 torsion, and there are infinitely many, so that this 2 torsion subgroup is a set 2 to the infinity. So the previous theorem says that in fact, these classes need to, infinitely many of these classes, or all but finitely many, have to lie in N1. So they all need to be supported divisors. And again, I can show you explicitly what these classes here are, but it's not obvious that they are supported in divisors. This is non-trivial. So this N1 here is infinite. And the conclusion is that the torsion in the Griffiths group is in general not finitely generated. Okay, so I have five minutes. So maybe I just say what are the classes here, and then I'll spend the rest of my time to talk over to which extent this works for other fields. So what are these classes here? On JC, on this Jacobian, we had the Theresa cycle given by the curve minus the image of the curve by the multiplication by -1 map. This was a curve class here that was interesting. And I can take the exterior product of that curve class with the canonical bundle of the Enrique surface. So the canonical bundle of the Enrique surface is 2 torsion. And if I take this exterior product, I get a surface class that is 2 torsion. And instead of looking at the Theresa cycle, I can look at the push forward of the Theresa cycle by some multiplication by n map. And this way I get infinitely many such classes. And the result here is that these classes are linearly independent. And the method, it uses refined unramified cohomology in a crucial way, but I don't have time to explain this argument, so I will skip it. Okay, and instead I want to, okay, the last 4 minutes to a little bit about other fields, because there is something interesting going on there, I think. Okay, so the story that I explained, most of it, what it needed to work was a cohomology theory, a Borel-Moore homology theory, in fact, with some basic properties. And this works essentially over any field K, at least if we work l-adically, so we fix a prime L invertible in K. Okay, and then I look at an algebraic K scheme with structure morphism pi x to spec K, and let D be the dimension. And now since K is an arbitrary field, l-adic étale cohomology doesn't work so well. So we need to use continuous étale cohomology. And since in fact I need Borel-Moore homology, it's best to work in the pro-étale side of Butt and Scholze. So this is the site where the opens are weak étale maps. And there is a 6-functor formalism, and there is a well-defined upper shriek, and we can take this upper shriek of set head L. Okay, so I don't want to explain exactly what that is, but it's essentially, you can think about it as a set L that we pull back from the point to X. And this is exactly the analogon of Borel-Moore homology. Okay, and then for finite coefficients, I write here also pro-étale, but for finite coefficients, I could as well just take the étale side of X and also apply the upper shriek to mu L to the R tensor n minus D. So this one is more classical. Okay, and then the cohomology of QL mod ZL twisted n is defined as usual as the direct limit of these cohomologies with finite coefficients. Okay, so what is written here are groups that behave what is written here is Borel-Moore homology, and they work exactly as Borel-Moore homology in the analytic case. So they have pullbacks for étale maps of the same dimension. They have push forwards for proper maps. There is a cycle class map, and so on. In particular, I can define the cohomology of fj of x as before. Well, now A is not an arbitrary abelian group, but A should be either ZL or this Z mod L to the R, and then I take this sheaf here. So for suitable A, for suitable coefficients, where these cohomology theories are defined up here, we can define the cohomology of fj of x again just as the direct limit, where we run over all open subsets that contain fj of x. And then the J's refined and ramified cohomology is defined as the image as before. All classes on fj of x that live to fj plus 1 of x. And in the setup, there is a cycle class map. So x, no matter how singular x is, there's a cycle class map tensor ZL. that goes to this group. And if X is smooth, then these groups here coincide with the continuous étale cohomology groups of Janssen, and this map agrees with Janssen's cycle class map. Okay, and so since the arguments well, I didn't really present the arguments, but I hinted at some ideas, and the arguments are quite formal and use only basic ingredients, and these ingredients are true in the setup, and for that reason we get analogous theorems in this setup. And here's the result. So X is over K, X is separated schema of finite type over K, L is invertible in K. The l-adic Chow group, meaning the Chow group tensor ZL, has a cycle class map to this Borel-Moore pro-étale cohomology group. And we would like to understand kernel and image, or kernel and co-kernel. And the theorem is that over any field, we can compute the co-kernel of that map in terms of some unramified, refined unramified cohomology, and also the torsion of the co-kernel, which is analogous to the formula that we've seen before, up to the fact that you have to put some L's somewhere in some tape twists. But otherwise, it's analogous. And this formula, I think, if X is smooth projective, then and I is 2, then this is due to Khan. And yeah, so this generalizes this to the singular setting and to arbitrary I. But now what is interesting is that if K is algebraically closed, then also the Griffiths group can be computed with similar formulas as I've shown you before, and there's a transcendental arbitrary copy map and so on. So over algebraically closed fields, the story is very similar to what I've shown you before. But over finitely generated fields, the story is different. So if K is finitely generated, then the kernel of the cycle class map, really from the Chow group, is computed by such a formula. So some refined and ramified cohomology mod some actual cohomology group. And there is again an arbitrary copy map from the torsion subgroup of the kernel of the cycle class map to some quotient of cohomology groups. And the kernel can be computed by refined and ramified cohomology. So what's new here is that over algebraically closed fields, or over C, this unramified cohomology business only computes Chow groups mod algebraic equivalence. But over finitely generated fields, the story is different, and it really computes Chow groups, not algebraic equivalence. And I think this is interesting. And what's also interesting is that, well, all these results underlie the same formalism, and in particular, the groups on the right look formally exactly the same. So, you know, if K was not finitely generated but algebraically closed, then this right-hand side wouldn't be the kernel of the cycle class map, but the kernel of the cycle class map mod algebraic equivalence. Okay, yeah, I don't state this because I think I have already stated enough complicated looking formulas. All right, so what's the upshot? The upshot is that refined and ramified cohomology groups l-adic Chow groups over finitely generated fields, and l-adic Chow groups modulo algebraic equivalence over algebraically closed fields. I stop here. Thanks.
Thank you. Questions or comments? So you can use the chat if you want.
Hello. So one technical question. How do you use the fact that Picard is equal to H1x étale GM? At some point you said you use Grothendieck's. Do you hear me?
Yes, I do. Yes. Yes, so it's used. Okay, so it's used to say that the H2 of a function field with ZL1 is torsion free. And this, so it's somehow a baby case of this Bloch-Kato argument that proves that the cohomology with ZL coefficients is torsion free. But in the case where the cohomology is in H2, one does not need Bloch-Kato, one needs the very, very baby case. And this is just the Kummer sequence plus Hilbert 90, which shows that, you know, the H1 of the function field is K star mod K star to the L, something like this.
Okay.
I think it's really just that.
So it's just Hilbert 90 for the function field, not.
Yes, but no, but the issue is that the way I defined this, it's not so clear that, or in fact, it's false. So it's not a Galois cohomology. This cohomology of the point, it's just this direct limit over all opens. And if you do this with finite coefficients, it's fine. But with l-adic, it's not fine.
Okay, and then there's another nasty question is there any hope to use this machinery to prove that some Chow groups are finitely generated over a field finitely generated over prime field?
I don't think so. But yeah. I mean, I agree. This looks, I mean, maybe you also had that thought. So that's at least the thing that comes to my mind is that if one looks at this formula here, say X is a surface and I is 2. So we are looking at points. Now, I would like to show that this is not too big if K is finitely generated. And this right-hand side, I know is very small if K is algebraically closed, because if K is algebraically closed, then this is the Griffiths group of codimension 2 cycles, and that's 0, because any 2 points I can join. They're all algebraically trivial. So over the algebraic closure, this guy here is 0. And I would like to say that this guy over a finitely generated group is not too big. Now, the issue is that since we have l-adic cohomology here, the direct you know, limits of schemes do not commute with cohomology. So I cannot just pull out this limit. Otherwise, we would get the result. So one would need to understand how this, yeah, one would need to see whether one can get around this difficulty.
Do you get something?
It's the same problem. It's the same. So for the finite field, the problem would be that direct limit and inverse limit don't commute. That's what one would have. That's the problem that what one has there. So one would need some way. Yeah.
Other questions?
Excuse me, did you try to relate these to T structures and weight structures maybe?
I didn't. No.
So I believe that this cohomology you consider corresponds to a T truncation of the object that represents, at least if your theory lives in some category with a good enough T structure.
So which groups do you mean? The Borel-Moore homology groups, or these guys, the unramified homologies?
Sorry, yes, I did not catch all of your talk. So I mean the image you consider Fi, I think you start with it, yes. So you can often describe this thing in terms of a T structure.
This one?
Yes, you should take, if you put your object corresponding to a theory into some triangulated categories, then there are often this T structure that gives a theory of this sort.
I see. Yes, I'm not aware of such a connection, but there could very well be. Yeah. Thank you.
So I will be glad to discuss it if you want it in future.
Yes. Okay. So you can do it. You can do it separately. Other question? Okay.
Can you say a little bit about the way that these refined unramified cohomology groups are used for rationality problems? to prove that certain varieties aren't
sure.
rational.
So actually there one needs unramified cohomology, because these refined unramified cohomology groups are not birational invariants. And this is just because cyclic groups are not birational invariants. But unramified cohomology, thanks to the work of Colliot-Thélène and Oyangur, it's a birational, stable birational invariant. And so what one has to do is one has to find some non-trivial elements there. And the way this is done is that it's k-theoretic. So one looks at the cohomology. First of all, one uses finite coefficients. So there is no hope to do this with integral coefficients. So you do it with finite coefficients, and then the cohomology of the function field is by Bloch just some Milnor K theory group. And so you try to find some symbol there that has no residues. And in K-theory, you can do these computations quite explicitly. And yes, so one hopes to find a nice variety where one finds a nice symbol that is non-zero and has no residues. And if one finds it, one wins, and one finds that that guy is not rational. And then there are some methods that allow to prove that also varieties that degenerate to this guy are not rational. So that's roughly speaking the way this works.
Okay.